All right, welcome back. So we are going to look at the next two chapters, 9 and 10, and they're both going to be considering electrons, basically, whether that has to do with their arrangements or the way they participate or the way they behave with chemical bonding. We're really going to focus on electrons now, so we're not going to be doing too much math, but we are going to be really getting into like electron arrangements. And so this is a big part of chemistry too. This is like this is the conceptual understanding of chemistry. So we're really going to go back into look into the models of the atom. We're really going to look at those again and analyze the electrons. And so for this chapter, starting out, we're going to look at two things right away. We're going to look at the electromagnetic spectrum and the Bohr model of an atom. Those two I put together. 9.1 and 9.2 are just like an introduction, but 9.3 and 9.4 really go together. So like we're going to talk about the electromagnetic spectrum and what that is and how that relates to the Bohr's model of an atom, because it led to the discovery of the Bohr model of an atom. And so those are two very related concepts, and that'll be the first model of the atom we look at. There is another one called the quantum mechanical model, which we'll look at next in the next video. And so let's just get right in. I'm going to go ahead and share my screen with you so I can look at my PowerPoint. So I'm going to be looking from the PDF that I uploaded to Google Classroom. You guys can scroll through this if you don't have your textbook at home. Hey, so this is cool, guys. Well, no, I shouldn't make light of this, but I love explosions, and this is sad that it caused the death of 36 people. But what an explosion this was. Man, I mean, the Hindenburg is quite the reaction. And so if you're not familiar with the Hindenburg, let me give you a brief little history. And if you're interested, you can go down a rabbit hole in Wikipedia, because there's a whole lot of information about the Hindenburg here. And I figured since we're doing distance learning, we wouldn't be just stuck looking at that boring picture in the book. Like automatically you can already see this picture here. Like what an incredible picture that is. Can you believe they caught that in 1937? They caught that on camera. Of course, because they were watching this thing land. There were people waiting for it, whatever. But just it's incredible that they have that. Can you imagine the photographer, whoever caught that, was like, man, he was set. So, and here's a video. I wanted to show you a video of what's going on here. So let me go full screen here. I don't know if I need the volume. So basically what you have here is a huge blimp full of hydrogen gas. This is the largest Zeppelin or blimp known that's ever been created. And we know you've seen the Goodyear blimp and all kinds of blimps up in the sky probably before in the Inland Empire at ball games or whatever. But those are usually full of helium, which is not reactive. This one's full of hydrogen, which is the lightest element on the periodic table. So it was a great, oh, look at that. Look at that. Oh my goodness. Watch the hydrogen burn. Watch. I mean, it's just blowing up and catching on fire. That is combustion right there. Oh, that is fire. That is fire. But not good. Look, you can see like people down there. There's a guy right there. One person actually died at the bottom. There were 35 people that died on board as passengers, and one person on the ground. But what an explosion. So that basically I think what happened is on the outside of the blimp, it caught fire through coming in through a storm or whatever. It was a transatlantic flight. It was a transatlantic flight from Europe going across the Atlantic Ocean, and it was landing in New Jersey. And I think there was a storm, so you can see it's kind of cloudy, and maybe that was caused some static electricity, and it caused a spark and maybe caused some of the outer layers of the blimp to catch on fire, like the fabric. And then once that happened, it lit the hydrogen gas that's inside the blimp, because that's what's combustible. That hydrogen gas is just like a bomb. So it kind of like blew up, but then the rest of the hydrogen, instead of being like a bomb, is basically just combusting here. It's just catching fire. But if this thing was super rigid, it would have blew up like a bomb. But since the fabric caught fire, basically the whole thing just combusted instantly. And look at the color. I mean, it's just like white light. Hydrogen kind of has that color. And we're going to talk about that in just a second now. So, but before we do the intro, the point of this intro was, what is the difference between a hydrogen blimp that does this and a helium blimp that helium's number 2 on the periodic table, and so it's also really light and works just as well. But why is helium inert and not reactive along with all these other gases that we call the noble gases, but yet hydrogen is so reactive along with all the other alkali metals that are in this column? This is group 1. This is the alkali metals on the periodic table. But hydrogen's also in that column just because of its electron arrangement. But it's not really a metal, right? Hydrogen's not a metal. So what's the difference there? That's what this chapter is all about, is trying to explain that difference of why hydrogen is reactive and helium is not. They're both lightweight and they're both great gases for a blimp, but one is a horrible idea for a blimp, and one is totally inert, as like neon, argon, krypton, xenon, and radon. Those are not reactive gases at all. They're totally satisfied with their electron arrangements and don't need any adjustments, whereas everything else pretty much needs an adjustment and is trying to be like the noble gases, whether they're gaining electrons or losing electrons. In this case, all of these guys are losing electrons to have stable electron configurations. Do you remember the octet rule? We've actually discussed a lot of this in the previous chapter, but we're going to look at these models again. The Bohr model, which is a little more simple, and the quantum mechanical model. That one's going to be in the next video. But before we discuss the Bohr model, it's important to note how light came about to be part of this discovery. And so, what is light to begin with? And so this is kind of a fun thing for me to teach. I love physics, and I like to think about things that kind of blow your mind, and this is one that blows a lot of people's mind. They don't really think about this, but light is essentially energy. Unlike any other thing we've discussed this year, it has no mass. You've been doing a lot of calculations with mass, and chemistry is all about particles that have mass, but light does not have mass. It's made up of photons that don't have mass, but they act kind of like particles, but they also act like waves. They're kind of weird. Photons are weird. But light is essentially, rather than a particle, it's energy. It's energy. Light is energy. That's why you don't really get light unless you have plugged something in. Unless you have a battery, you're not getting light. Unless you are using mechanical energy, whether it be running water over a turbine to turn a wheel, to turn a motor, to then generate energy, or it's wind to turn a motor, to turn a fan to turn a motor, or whether it's a battery that has chemical potential energy stored up in it. Remember, energy is not created or destroyed, and light is just one form of energy. And so basically, light is a form of just electromagnetic radiation. We have, in just a second, we'll talk about this large spectrum of electromagnetic radiation, and visible light is only just a small portion of it. You have radio waves, microwaves, X-rays, gamma rays, and so on. Light is just a small portion of that spectrum of energy. So it's just energy. It's a type of energy that travels through a constant speed. It's 3 times 10 to the 8 meters per second, or 186,000 miles. I'm sorry, miles a second. That is fast. Light travels very fast. That's why if you see a firework in the air, you usually see it before you hear it, because sound doesn't travel that fast. Light travels a whole lot faster. And basically, light always travels at that speed, at least in our atmosphere. And what we can do is we can characterize light by looking at its wave. And so what the most important thing about a wave is its length. And the way you measure wavelength is from crest to crest. All right? You're not looking at from crest to the trough. Hold on. sorry. You're not looking at from crest to trough. A lot of people will think that's the wavelength right there, but you're looking from crest of one wave to crest of the next wave. So if you're surfing, it's basically like you're looking at what is this distance between one wave and the next wave, the top of one wave to the top of the next wave. What is that distance? That would be a wavelength. Surfers like it when the wavelength is short, because that means many waves are coming their way. They also like the amplitude to be high, but then we're not discussing amplitude in this lecture. Wavelength, the length from one crest to the next crest, is very important when it comes to electromagnetic radiation. It basically determines the power, how much energy is in the wave. All right, and so that being said, let's talk a little bit more about wavelength, for example, in light. If you have a light source, let's say it's just like a white light, so a nice full spectrum light bulb that's just strictly white light. If you pass it through a slit, so you're basically just organizing the light so that it's all kind of going in one nice and neat line here, instead of being scattered all throughout like this big triangle here and going up, down. You got it going through a slit, so it's all going one direction here in a straight line. And then you pass it through a prism. What happens is well, here I have it gets separated into the many colors of the light, because white light is all the colors. And so I have a little image here. I kind of like this distance learning thing. It's allowing me to use technology a little bit better. White light's coming in, and when it hits the prism, the red wavelength is a lot longer, and so it actually travels nice and easy. So it actually travels very fast, so it doesn't get bent very much. It just quickly passes through the prism. But the blue light and the purple, the high energy light that has the really short wavelengths, they're traveling a little slower because they're doing all that bouncing up and down. There's a lot of energy in that wave, but it's traveling slower, and because of that, it gets bent more. Instead of going straight up like the red, it gets bent more and slowly bent. And so by the time all the light comes out the other end of the spectrum, it's been separated essentially into the different colors. That's all color is light at a certain frequency. I'm sorry, at a certain wavelength. And so this is interesting. A lot of people, this is where people's mind get blown about light and color and all this. It's really interesting. If you look at the shirt you're wearing right now, look at what color it is. That color is not really on your shirt. And if you don't believe me, turn out the lights. Do you see any color? No, because there's no light. The only way you're going to see color is if you see light, because the way our eyes work is we have receptors on the back of our eye that translate that wavelength of energy to a color, right? There's a lot of organisms that God didn't create to see color, and so, but we do. We have a special, and some people see color better than others, and some people have defects there, and will see different colors that they shouldn't see and stuff like that. And so, but here's what people often forget. They think that the color they're looking at, that color is there, like in the material. No, that color is not there. If you're in a really poorly lit room, everything just seems kind of grayish. And then you flip on a really nice light, and you're like, oh man, I didn't know that color was actually there. And so it's a good idea when you put your clothes on in the morning, or when you pick out your outfit in the morning, that you turn on the lights in your room so you can see what color outfit you're picking. Because once you get out into the light, you'll see colors pop a whole lot better. And so how are you going to get colors for what they really are? You need all the colors of light coming in. And then whatever is reflected, because some of it's going to get absorbed by the material. In this case, the leaf is absorbing pretty much all this light, but it's reflecting green light. And so that's why you're going to see green light when you see a leaf. The leaf is not absorbing this wavelength of light. It's reflecting that wavelength of light. So what color of light do plants like? A lot of people will say green, but it's no. They like every other color. In fact, specifically, they like red and blue. They like red and blue, and they don't like green. That's why they reflect it to your eye. And so if something is reflecting back red, that means that it's absorbing all the wavelengths of light that you're giving it, but it's reflecting red wavelength of light back to your eye. Does that make sense? Pretty interesting. Back to the lesson here. So if you take white light and you separate it, you should see all of the different wavelengths of light, because white light, if it's true white light, it's going to have it all. Like the sun is good for that. But if you try to use a light source that, is like a black light or a yellowish light or a bluish light, it'll mess up the colors that you're looking at. Like a black light makes everything look really weird. Like white shirts really look funny, and actually they look really cool in black lights. So depending on your light source, that's going to really help out with your colors. And that's why photographers and videographers are so picky about what lights are in a room for a concert or a wedding or whatever before they try to capture that light, because that's all photographers do, are essentially capturing wavelengths of light onto a device. Okay, and so again, white light's responsible for all the colors we see, because it provides all the wavelengths necessary for our eye to see, and then whatever, again, is only reflected back to our eye is what we see. And light waves are characterized by their frequency. By the way, we use this little letter, the Greek symbol nu. It's like a V that represents frequency. Up here, when we talked about wavelength, we use the Greek symbol lambda. It looks like a A, but it's not quite an A. It kind of comes up a little bit. That's a Greek letter, lambda. That lambda represents wavelength. Wavelength's more important. Frequency is just basically how many wavelengths pass through a stationary point in 1 second. So how many of these wavelengths will pass through, or like if you're a surfer standing here or sitting in the water, and you're watching the waves are coming by you, how many wavelengths per second pass the surfer? That would be the frequency. Frequency is like a duration thing. It's like how many. It's per time. It's basically wavelength per time. And they're inversely related. The shorter the wavelength, the higher the frequency, right? If you have a really short wavelength here, a lot of wavelengths per second are going to pass, right? If you have a long wavelength, the frequency is going to be really low. You're going to have a low frequency because you're going to have a low number of wavelengths that actually pass through you per second. All right? And so stay with me here. So blue light has the highest frequency. You need to know these terms and how they're related. In the early 20th century, the scientists figured out that energy in a light acts almost like a particle, like a stream of particles. And we call those photons. And you can basically think of those photons as like a single packet of light energy. And the amount of energy that's carried in that little packet depends on the wavelength of the light. So check this out. Again, these are the terms you need to know and how they're related to each other. The amount of energy in the packet depends on the wavelength. The shorter the wavelength, the greater the energy. Just as water waves carry more energy if the crests are close together. Think about surf pounding the beach. Light waves carry more energy if their crests are closer together. Therefore, violet light or purple has the shorter wavelength, carries more energy per photon than red light, which has the longer wavelength. So red light has a less amount of energy. Sorry, I was looking for a better image there. Red light, not very energetic. Blue light, super energetic. Let's just go back to this. How about that? You see how the red wavelengths are longer? If you look at the blue and the purple or the violet wavelengths, they're a whole lot shorter. So shorter wavelengths mean higher frequency and higher energy. So blue light has a whole lot of energy, Blue light has a whole lot of energy, and it looks that way, right? Think about going up and down, up and down, up and down, up and down a whole lot, right? That's a lot of energy. A wavelength that's only carrying, like the red, only carrying so many wavelengths per second. Just it's a low energy wave. It's a low energy wave, and they actually travel quite fast because of that, right? There's not much going on, so you can travel in a straight line pretty fast. But these guys, these blue ones, they're so energetic that they're spending so much time going up and down. They're so energetic that the blue light actually travels slower, but it is more energetic. Okay, so again, think about the terms. Short wavelengths with the blue light, short wavelengths, high frequency, high amount of energy. So now let's go back to our diagram, and let's look at the electromagnetic spectrum. So here's our entire electromagnetic spectrum from long wavelengths to really, really short wavelengths. And let's just analyze this whole thing for a second. By the way, these numbers here, 10 to the 5th, 10 to the 3rd, 10, these are in meters. These are wavelengths in meters. So we're measuring the wavelength here of this energy. So this is called electromagnetic energy. And again, light is only right here. It's from like times 10 to the it's in between times 10 to the -5 and times 10 to the -7. So it's like times 10 to the -6 meters. So basically nanometers. And here it is. If you take this little band of nanometers wavelength of radiation, you have visible light. Anything outside of that, you can't see. You can't see infrared unless you have special eyes that are engineered by humans that will allow you to see it. Then you can do that. You can't see X-rays. You can't see gamma rays unless, again, you have devices that can translate those to images that you can see. But our eyes can only see visible light in this little short region here of wavelength. And if you want to zoom in to this little spectrum, you can do that, and that's what they've done here. They've zoomed in, and remember, so here we're going from low energy waves to high energy waves. From left to right, we're going from low energy, long wavelengths, low energy, to short wavelengths, high energy. And so further to the left is the red. Red has a long wavelength, 750 nanometers. That's long compared to 400 or 450 of the blue or purple. And so since these wavelengths are shorter, blue and purple have higher energy than red. Green has more energy than yellow. Yellow has more energy than red. Green has less energy than blue, and so on, as far as the visible light. But again, let's look at all the different waves, at least just the ones that are on this table here, or this figure. Radio waves. Are those important? Do we still listen to the radio? Absolutely, we still listen to the radio. Do we tune into AM radio waves and FM radio waves? Absolutely. By the way, those numbers represent frequencies that you tune into your station, like 89.7. But radio waves, believe it or not, are actually what power our cell phones. So when you send a text message or you're using data from your cellular networks, there's cell phone towers that are emitting radio waves to your cell phone, and then your cell phone also emits radio waves back to the cell phone tower. And so all of our phones are constantly pinging off of cell phone towers all around us, and there's a huge network of cell phone towers that emit radio waves. And so that's why radio waves are almost like patented nowadays. Basically, you don't want to be on a frequency of radio waves that the cell phone companies are using, because you're interfering with that. That's why a lot of the microphones that we use in like chapel, or for like I'm gonna say it, class challenge, we get like a lot of problems with like during class challenge, because like the microphones are on some frequency to communicate with the wireless. We're talking about the wireless microphones, not the wired ones, but the wireless ones use radio wave technology. And if that frequency is the same as the cell phone companies, you're going to end up with interference and problems. And so that's why the cell phone companies are actually trying to get all of those wireless mics to use different frequencies, and they're going to be regulating that a lot more soon. So anyways, radio waves. But there's a lot, you can see this. You have from 10 to the 5th meters to 10 to the -1 meters, which is 1 meter. You have a huge spectrum of radio waves that are available to us to use. Okay, now more energetic waves. Let's go to microwaves. Microwaves, not that harmful. Not that harmful. They're short wavelengths. No, long wavelengths, but low energy. Infrared radiation also has low energy. Visible light also doesn't really have a whole lot of energy. Not really dangerous. Now, when you get into UV radiation, which is still coming from the sun, that's actually kind of harmful. UV radiation can damage your DNA with all the energy. Same with X-rays and gamma rays. As we go up the list here, these wavelengths of energy have so much energy. Short wavelengths, but high amount of energy, high amount of frequency. That energy can actually destroy DNA molecules and cause mutations and lots of trouble. You can have a lot of issues when you're around these kind of radiations. Okay, but this is all one spectrum. This is all one spectrum of one type of energy, electromagnetic radiation. Okay, now why is basically I just read all of this. Instead of reading it, I summarized it. Why is all this important to the atom? You can answer some of these questions yourself. It's all based on the amount of the material I just gave you guys, comparing wavelengths and frequencies and energies. But I want to move on to the Bohr model of atoms. Why is this important for the Bohr model of an atom, and how did it lead to its discovery? So here's something kind of cool. When an atom absorbs energy, whether that be from heat, light, or electricity, you can actually just run electricity through an atom and it'll energize it. When it does that, it usually re-emits that energy as light. For example, a neon sign. You've probably seen neon signs around town. Sometimes they're still popular. They used to be back in the 80s and 90s. But basically what happens is an electric current is passed through a tube. And in that tube, there's gases like neon gas or argon gas. And those atoms of neon or argon or whatever, they're going to absorb some of that electrical energy, and then they're going to re-emit. They're going to re-emit that energy as light. And so depending on what atom you're using, like neon or argon or helium, you're going to get different colors because they're all going to re-emit different amounts of energy. And so this is interesting. In a given element, what we noticed was that there would be unique colors or unique wavelengths of light that those atoms would release. Well, so what does that suggest? That suggests that something is going on with the electrons and the amount of energy that they're consistently releasing within a particular element. And so let's look at this situation here. Same situation we just looked at with the prism and white light. But this time, instead of using white light, let's say we had a hydrogen lamp. So we had a bunch of hydrogen in here. We just learned that putting electricity around hydrogen was a bad idea. But here it's contained. And so there's no oxygen because you can light hydrogen all day long with electricity and it's not going to catch fire unless you have oxygen. So this is like a vacuum sealed tube with no oxygen present, so no combustion. But it is going to energize the hydrogen. The electricity in this little glass tube is going to energize the hydrogen gas that's in the tube. And so you can do the same thing. You can run it through a slit so it's all going nice and neat, one way, single file line. You can run that light through a prism and then separate it. And this time you're not going to get the white light spectrum, but you're going to get a different spectrum. And in fact, this is like a fingerprint. This is like a fingerprint for hydrogen. Because basically, every time you energize hydrogen, we always get this situation. We always get this red light, which is a certain wavelength. We always get this wavelength of blue light and this wavelength of purple light, and no other lights, no other wavelengths. So how are we getting this consistent, exact amount of light in these bands when we put a little photographic film here to capture that? We get these bands, almost like fingerprints. So here's hydrogens, here's heliums, here's neons. Each atom has its own, what we call, those are called emission spectra. So this is an emission spectrum. Every atom has its own emission spectra, which is unique to that element. And so what does that suggest? Well, basically, what that suggests is that we have some consistency here that's relating to quantum mechanics, basically. So let me explain this. So here we have an atom of, I guess it's hydrogen here. Well, it doesn't matter. We have a nucleus where all the protons are. We're not concerned with the protons right now, but there it is. And then we have these orbits where electrons orbit, kind of like planets around the sun. We pretend the nucleus is the sun, and the electrons are orbiting around the nucleus like planets orbit around the sun. But these are very quantized. And what's happening here is that as an electron is energized, it jumps to a higher orbit. So the way these orbits work is N1, the first orbit, this has the least amount of energy required to be inside of it. To be in the fifth orbit, you need a whole lot of energy. And so when you energize an atom, the electrons can actually go to higher energy orbits. Like let's say an electron was in energy orbit number 2. It would jump to the third energy level, but nothing in between. There is no in between. So these energy levels are kind of like steps on a ladder. You can't step on a step in between step number 1 and step number 2, can you? It's impossible. It's the same way with electrons. They can only go from one orbit to the next. It's very quantity, like a number. It's very specific. It's a number that doesn't change. And if we energize the electron and we make it go from energy level number 2 to energy level number 3, remember we said that that's not very stable for the atom, and that the atom is going to re-release that energy as light. And when it does that, the electron is going to fall back to the second energy orbit. And then however much energy that takes to go back to the relaxed state, because when the electron's here in the energy level 2, it wasn't absorbing or emitting any light. But you energize it to 3 by giving it energy, and it's going to fall back to the relaxed state. And when it does, it's going to release this amount of energy, 657 nanometer wavelength of light, which is red. It's a very specific amount of energy. That's a very specific color. And that specific color literally tells us that there's 657 nanometer wavelength of light. So there's that much energy required for this electron to fall back to orbit level 2 from the third level. Now, if you're this electron and you're at the second level still, and you get energized to the fourth level, that's even higher amount of energy, and then you fall back 2 energy levels back to level number 2, then that amount of energy, that quantized amount of energy, is 486 nanometers of wavelength of light, which is bluish green. Now, if you're going to excite an electron all the way from the second energy level to the fifth energy level, and you allow it to fall back to the second energy level, remember, it's going to re-release that energy. Energy can't be created or destroyed. It's got to go somewhere. You just energized the electron up to here. When it falls back, it's going to re-release that energy as light. And that this time it's 434 nanometers. It's a shorter wavelength. But remember, shorter wavelength means higher energy. So that's a lot of energy. And so what Niels Bohr discovered was that when you energized atoms, you would get these bands like this that are consistent. Hydrogen always makes this spectrum. Helium always makes this spectrum. And so these differences here these differences here are a result of very, very specific energy levels that the electrons are moving between. All right. Now, the only thing that the Bohr model didn't do a great job at was explaining how what would happen if you were in the atom contained like more than one electron. And so for this and other reasons, the Bohr model was replaced with a more sophisticated model called the quantum mechanical or wave mechanical model. And it has to do with what we're just talking about, though. Quantum mechanics has to do with the fact that there are these quantum or quantized amounts of energy between energy levels of electrons. All right, so again, as it does so, it releases a photon of light containing the precise amount of energy called a quantum of energy. So the energy of each Bohr orbit is specified by a quantum number, which we'll call 1, 2, or 3, and those are fixed. They're quantized. They're fixed. Okay, they're not changing. And the energy of each orbit releases, or the energy of each orbit increases with increasing value of n, remember? And so you can reread all this if you want, but basically I summarized it by looking at these pictures. I'm a very visual person, so here's another good one. We didn't look at this figure. Basically, when energy is absorbed by the atom, so you see energy absorption, energy is coming in, and this electron gets excited, and it goes from N1 to N3. Well, when it gets relaxes, it doesn't actually have to relax all the way back to 1. It depends. If you're still energizing the atom, then the electron's only going to maybe relax back to level 2. But whatever, if it relaxes, it's going to be releasing some light. And when it does that, going from one level to the next, or going from one level to 2 levels away, is always going to release a certain amount of energy. The electron does not fall back to some middle level here in between orbits. Can't do that. These are quantized orbits. Okay, we have 1, 2, 3, 4, 5. We're going to look at how the electrons occupy these shells throughout this chapter. But to summarize what we've learned in this video and in this lesson, remember that electrons exist in quantized orbits at specific fixed energies and specific fixed distances from the nucleus. Okay, when energy is put into an atom, electrons are excited to higher energy orbits, further away from the nucleus. When an electron relaxes or falls from a higher energy orbit to a lower energy orbit, the atom emits light. Because remember, light is energy. And you can measure that energy by the wavelength of light or the color of the light. The energy, I guess that's this last point here, the energy and therefore the wavelength of the emitted light corresponds to the energy difference between the two orbits in the transition. Since these energies are fixed and discrete, the energy and therefore the wavelength of emitted light are fixed and discrete. All right? Since these orbits are a certain distance away from each other, when the electron falls back from one to the other, it's always going to be a very specific amount of wavelength of light, a very specific amount of energy, in other words. So do you see how all this is related? How light is very related to us understanding these quantized orbits? In the next lesson, we're going to look at the quantum mechanical model of atoms. And instead of talking about orbits, we'll talk about orbitals. And so, all right, hopefully you guys got a good understanding of that. If not, chime in to the Zoom meetings and I can help you with any questions that the book is asking you regarding that stuff. Bye-bye.